Hello everyone, welcome to Reactify Labs. In this video, we will talk about ZNodes. In the last video, I mentioned that ZNodes are present in ZooKeeper, and I had also promised that I would make a separate video on ZNodes. So this is that video. Okay. So before we start, let's see the structure that we are going to follow today. So first we will see what are ZNodes. Then we will see what are the types of ZNodes. Next, we will see the leader election process in ZooKeeper. Okay, because ZNodes are involved there, that's why. Next, we will see the metadata present in ZNodes. Then we will talk about the operations that happen on ZNodes. After that, we will talk about ZNode paths very briefly. After that, we will see security and ACL. ACL is access control list. Okay, and then we will see the use cases and examples. Okay, so this is the structure that we are going to follow today. So yeah, now that everything is ready, let's start with the introduction. What are ZNodes? So ZNodes are basically the fundamental data structures in ZooKeeper. So they are fundamental data structures in ZooKeeper. So they are fundamental data structures in ZooKeeper, which serves as the nodes of hierarchical namespace that ZooKeeper manages. Okay, serving as the nodes of the hierarchical namespace. Hierarchical namespace that ZooKeeper manages. Okay. Each ZNode can be thought of as a file or directory in a traditional file system, but with specific characteristics and capabilities tailored for distributed systems. Okay. So the key characteristics are, first one is hierarchical structure. ZNodes are organized in a tree-like structure where each node can have one parent and 0 or more children. As I talked about this in the ZooKeeper video also, that this is the root and anything after this is just like the directory structure that we have in our computers. Okay. Next is data storage. Each ZNode can store a small amount of data, usually up to 1 MB. This data is associated with the ZNode itself, similar to how a file in a file system might contain data. And metadata. ZNodes contain metadata such as version numbers, timestamps, access control lists, and a lot of things. This metadata is used for managing the state and control access to ZNode. Okay. Next, we will see the types of ZNode. So we will see what are the types of ZNodes. ZNodes have different types. Actually, there are 4 types of ZNodes. Okay. So first one is persistent ZNodes. So persistent ZNodes are the most straightforward type of ZNode. They remain in ZooKeeper's tree structure until they are explicitly deleted by the client that created them or by another client with appropriate permissions. Okay. Like they persist across different sessions, meaning they stay in ZooKeeper tree even if the client that created them disconnects or crashes. Persistent ZNodes can have children, allowing for hierarchical data storage, and they are ideal for storing configuration data, application state, or any information that needs to be retained across sessions. For example, a distributed application might use a persistent ZNode at, let's say, the location in the root, it's in config and application. Okay. So this location might be used to store global configuration settings. So this ZNode remains available even if the application restarts. Okay. And a file system like hierarchy could be represented using persistent ZNode, such as app data config for different levels of configuration data. Like inside this app, there will be data, there will be config. Okay. So this holds the configuration of data. Let's say we need some other configuration. So we can have another folder like structure, right? So this is what is the structure. Okay. Next is ephemeral ZNodes. Ephemeral ZNodes. So ephemeral ZNodes are temporary and are automatically deleted when the client that created them disconnects or its session expires. They are useful for managing transient states. So they are tied to the client's session. If the client disconnects or the session times out, the ZNode is deleted, unlike the persistents. Okay. In the persistent ZNodes, they were not deleted even if the client left, right? So ephemeral ZNodes cannot have children. They are always leaf nodes. Okay. And they are suitable for representing temporary state or service registration. A microservice might create an ephemeral ZNode, let's say in the services folder, it's like this, services slash service S1. Okay. So it can register itself. If the service crashes or shuts down, the ZNode is removed, signaling its absence to other services. So this can be removed. Okay. An ephemeral ZNode might be used to indicate that a lock is held. For example, let's say if we have a locks directory and let's say lock L1 is used. So this is basically an ephemeral ZNode, right? So it might be used to indicate that a lock is held. If the process holding the lock fails, the ZNode is automatically deleted, which releases this lock. Okay. Next is sequential ZNodes. Sequential ZNodes. So the sequential ZNodes are used to create a sequence of nodes with unique incrementing identifiers. They help in maintaining order and uniqueness. ZooKeeper appends a sequence number to ZNode's name, ensuring uniqueness. The sequence number reflects the order in which the ZNodes were created. They are useful in scenarios where order of operations or uniqueness is important. So, for example, tasks might be added to a queue by adding sequential ZNodes under tasks. The ZNode names determine the order in which tasks are processed. Okay, let's say for example, we have a tasks directory. And let's say task 00001. Okay, there is another in the same tasks directory T00002. So this is sequential. So depending on the number, they will be processed. Okay, so first this one will be processed, then this one will be processed. Okay, so this is what it will follow. And there is one more, which is a combination of ephemeral and sequential. Okay, and this is called ephemeral sequential ZNodes. Ephemeral sequential ZNodes combine the properties of ephemeral and sequential ZNodes. They are temporary and uniquely identified with a sequence number. They are automatically deleted with the client session and include a sequence number for uniqueness. They are ideal for leader election or scenarios where unique temporary identifiers are needed. Okay. In a leader election process, clients create ephemeral sequential ZNodes under election folder, okay, election directory. The client that creates the ZNode with the smallest sequence number becomes the leader. If the leader's session ends, its ZNode is deleted and a new leader is elected based on the next smallest number. For temporary tasks that need unique identifiers, ephemeral sequential ZNodes can be created. For example, a temporary resource allocation might use ZNodes like, let's say, some resource R1 to ensure that each resource request is uniquely identified and managed. Okay, so each resource will be named like this: R1, R2, R3, something like this. Okay, so let's see now the leader election process, how that is done. Okay, so leader leader election. So imagine you have a cluster of servers where one server needs to act as the leader to coordinate tasks among the others. But if the current leader fails, a new leader must be elected quickly to ensure that the system continues to operate smoothly, right? So if we have multiple nodes, one of them must be the leader, okay? Because followers follow the leader. If leader is not there, so whom will the followers follow? So they have to appoint a new leader, right? So this is what it is. So what are the steps? First step is nodes compete for leadership. Nodes compete for leadership. Each node in the cluster attempts to become the leader by trying to create a special ZNode in ZooKeeper. Let's say in the election folder, node is called leader is created. Okay, the creation of this ZNode is atomic, meaning that only one node will successfully create it and the rest will fail. Okay, step 2 is identifying the leader. Step 2 is identifying the leader. The node that successfully creates the leader node, like this ZNode, becomes the leader, right? This node then performs the necessary leadership tasks, such as coordinating tasks among other nodes. Okay, it will start acting like a leader. Next is leader failure detection. Leader failure detection. If the leader node fails, for example, let's say it crashes or loses connection, ZooKeeper automatically deletes this. Okay, ZooKeeper will delete this folder which was created by that node. Okay, now what happens is ZooKeeper, now the other nodes in the ZooKeeper, the other nodes that are present, they will again compete for the leadership, right? So what happens is, if the leader node fails, ZooKeeper automatically deletes this leader folder. Actually, yeah, ZooKeeper deletes this leader folder. Okay, because it is ephemeral. Okay, it is ephemeral because since the leader went down, as I told you in this ephemeral ZNode, the leader went down. So this folder was created by that leader, and that's why it also gets deleted, right? So if we have, let's say, multiple nodes, this one had created the leader folder, and since this one is down, so this one also gets deleted, right? Now next step is re-election. Upon detecting the deletion of this folder, detecting the deletion of this folder, leader ZNode, actually not a folder, the right name to use here is the ZNode. Okay, upon detecting the deletion of the ZNode, leader ZNode, the remaining nodes again compete to create the ZNode. A new leader is elected and the system continues to function without interruption. So once this one goes down, it means this got deleted. Then the other nodes will again start competing that, okay, let's create the ZNode. So everyone will start creating this in the election directory. Everyone will start creating a leader ZNode. Okay, and as I mentioned, this is atomic. This is an atomic operation. So everyone will attempt, but only one will succeed. And since that node will succeed, whichever node succeeds, let's say this node succeeded, then this will become the leader. Okay. Now again, when this goes down, again this folder will be deleted. Basically this one. Again, when this goes down, this will be deleted. And once this is deleted, again they will start competing. Okay. So this is what happens. This is the leader election process in the among the ZNodes basically. So it's like a classroom where a monitor is decided by the show of hands, like whichever person showed hand the fastest or whichever person raised the hand the fastest, they become the monitor, right? Okay. Next, let's talk about the metadata in ZNodes. Metadata in ZNodes. So every ZNode in ZooKeeper has associated metadata that provides information about its state and usage. First is versions. ZooKeeper maintains version numbers for each ZNode, including data versions, ACL versions, child versions. So data versions tracks changes to ZNode's data, ACL versions tracks changes to ZNode's access control list, and child version tracks changes to ZNode's children. Version numbers are used for optimistic concurrency control, ensuring that updates to a ZNode's data or structure are applied correctly. So for example, when updating a ZNode, a client can specify the expected version number. If ZNode's version has changed since the client's last read, the update fails, okay, preventing conflicting updates. Because if obviously, if let's say there is a version 1, okay, there is version 2, and let's say the latest version is version 4, okay, and if somebody says, okay, go and update version 1, it will be rejected because it's outdated information, right? Next is timestamps. Timestamps. So ZooKeeper records two timestamps for each ZNode. First is creation time, second is modification time. So creation time is the time when the ZNode was created, and modification time is the time when the ZNode was last modified. And if we talk about the use case, timestamps can be used for auditing and tracking changes to ZNodes. For example, in a distributed application, you might use the modification time to determine how recently a configuration setting was updated, right? So let's say current version is v4. So along with this, there will be a modification time also, or not with version, basically with a node. Okay, so here in some folder, some node is created. what is the modification time and what is the creation time. So we can see that creation time may be 1 year ago and modification time was, let's say, 1 second ago or few seconds ago. Okay. So because we need to know how relevant the information is, it's possible that the modification never happened, right? Then we might know that, oh, okay, there may be some problem. Either the modification never happened actually in the system, or this node is not receiving the updates. Okay. So that's why it's important. Next is data length. Data length. It indicates the size of the data stored in ZNode. As I told you in the beginning also, the maximum size that ZNode can store is 1 MB usually. Okay. It helps in managing and optimizing the storage of data in ZooKeeper. If a ZNode's data length exceeds the recommended size is 1 MB. If the data length exceeds that, it might be a sign that the application needs to store less data in ZooKeeper or offload the data to another system. Okay. And next is number of children. Number of children. So it reflects the number of child ZNodes under a given ZNode. Okay. It's useful for understanding the structure and the scale of the ZooKeeper tree. For example, in a distributed queue, the number of children under the tasks directory node can indicate the number of tasks currently in queue, right? For example, let's say that there is a task directory. So it can have multiple files, right? It will tell you how many tasks are there in the queue. What is the size, or what is the level of task that ZooKeeper needs to handle. Okay. Great. Now let's talk about the operations on ZNodes. Operations. So ZooKeeper provides various operations for interacting with ZNodes. First operation is create. Create operation creates a new ZNode in the ZooKeeper tree. The operation specifies the path, data, and the type as in like type of ZNode, persistent, ephemeral, sequential, or whatever, right? It is used to add new data or state to the ZooKeeper tree. A client might create a new ZNode at, like, let's say a location, okay, with the value enabled to store new configuration setting, right? Let's say in the config directory, it creates a new ZNode called new setting, okay? And here in the new setting file, it has something like enabled variable to true. It means the new setting is applicable now. Okay. Next is read. First one was create. Next the read. Read is similar to get data basically. So it retrieves the data stored in a ZNode along with its metadata. It is used to read configuration settings, application state, or any other data stored in ZooKeeper. For example, a distributed application might read the value of app setting to determine whether a specific feature should be enabled or not, right? So let's say in the config directory, there is a directory called, or this ZNode called app setting, right? So here you can read this app setting file to know if any other variable, let's say variable XYZ, is true or false or whatever the value it is, right? Okay. Next is update. Next is update. Okay. Update means set data basically. It updates the data stored in a ZNode. The operation can also specify the expected version number to ensure that the update is applied correctly. Okay. It is used to modify the data stored in ZooKeeper, such as updating configuration settings or state information. An administrator might update the value of app setting from enabled to disabled to turn off a feature in the application. Again, same example. In the config folder, if we have, let's say, app settings, and in this settings file, basically this is ZNode, which is a file. If there is a variable for which its enabled was true, it can just set it to false. Okay, this is update. Okay, and next is delete. As the name suggests, this will delete something. It deletes a ZNode from the ZooKeeper tree. A ZNode must be empty. That is, it should not have any children before it can be deleted. It is used to remove data or state that is no longer needed. After a feature is permanently retired, the associated configuration setting at those directory levels might be deleted. At those ZNodes might be deleted, right? Next is watch. 5. ZooKeeper allows clients to set watches on ZNodes. A watch triggers a notification when the ZNode is changed, deleted, or has children added or removed. Watches are used to react to changes in the ZooKeeper tree, enabling event-driven behavior in distributed applications. A client might set a watch on the app setting directory or the app setting ZNode to receive a notification whenever the setting is changed, allowing the application to dynamically adjust its behavior, right? Again, if we take the example of config/app setting, so if a watch is set up on this, so any change which happens to this will be considered as an event, and this will trigger the notification, right? Event driven architecture or event driven behavior. Okay. Next, let's talk about ZNode paths. ZNode paths. Already I have discussed this in this while explaining other things. So let's talk about it in brief. ZNodes are identified there by their paths, which follows a Unix-like syntax. Okay, this Unix-like syntax. So there are absolute paths. All ZNode paths in ZooKeeper are absolute because everything starts from this. This is the root, right? This is root. Everything starts from this. ZNode names can include alphanumeric characters, dots, dashes, and underscores, but must not include null characters or slashes, right? So it can have A to Z, A to Z, 0 to 9, dots, dashes, underscores, but obviously it cannot have this slash because it represents the change in the folder structure, right? So that's why it cannot have slash or nothing. Okay. So for example, again, this, let's say config/c1, it refers to the specific configuration setting. Okay, basically it's better one would be app setting. Config/app setting, it refers to a specific configuration setting. And let's say in the tasks directory, if it's, let's say, task 00001, so it refers to a specific task in a distributed queue. Okay. Okay, now that we have talked about ZNode paths, let's talk about the security. Security and access control lists. Okay, so ZooKeeper provides an access control list mechanism to manage permissions on ZNodes. Okay, so what are the ACL components? So ACL components define the type of authentication, okay, such as world, which is open to all, auth, which is authenticated users, or digest, which needs username and password. Okay, so there are three things: world, auth, and digest. Okay, so if some kind of configuration is defined as world, it means everybody can access that. If it's auth, it means only authenticated users can access that. And if it's digest, it means you have to enter username and password to access that. So the identifier for the entity user is the ID that the ACL applies to. Okay, basically ID is the identifier for the entity user that the ACL applies to. Okay, and the specific actions allowed, like read, write, create, delete, and administer. Okay, read, write, create, delete, administer, these are the options or actions that are allowed. Okay, so for example, a ZNode with an ACL of, let's say, world, actually wait, let it be. Okay, if it's ACL of the ZNode is like this, world, and in that it's anyone, this it's R, it means it allows anyone to read the data. Okay, it allows anyone to read the data, but not anyone can write it because it does not mention anything about write, right? Okay, so distributed application might store sensitive configuration data in a ZNode with a restrictive ACL, ensuring that only specific clients can modify it. So if there is sensitive data, it might be inside the auth, right? Or digest somewhere, right? Okay, now that this is done, let's talk about the use cases and examples. Use cases and examples. Okay, so ZNodes are used in a wide range of distributed system scenarios. First one is service discovery. Service discovery. In a microservices architecture, services might register themselves by creating ephemeral ZNodes under services directory. Other services can discover available services by reading the children of services directory. Means this. Okay, every service can create its own ZNode in this directory, and anybody needs to identify something, it will read inside this service. Okay, next is configuration management. Configuration management. A centralized configuration management system might store settings in persistent ZNodes. Clients can read these settings on startup and react to changes using watches. Okay, next is leader election. Leader election. In a distributed system requiring a leader, for example, for coordination, clients might create ephemeral sequential ZNodes under leader election, right? The client with the smallest sequence number becomes the leader. As I said, in the election directory, it can create a folder named leader or leader election or something like that, right? And whoever creates first becomes the leader. And next is distributed locks. Distributed locks. So to implement a distributed lock, clients might try to create a ZNode at a specific path. The clients that successfully creates the ZNode holds the lock. If the ZNode already exists, other clients must wait until it is deleted. For example, again, in the logs directory, whichever client creates the, let's say, lock or my lock or shared lock or whatever, the name can be anything, but whichever node or whichever client is able to successfully create this ZNode holds the lock. And if, like, let's say somebody is holding this lock and somebody else comes and tries to create its own, let's say, iLock, okay, something like this, then this client needs to wait until this lock is deleted. That means the other client releases its lock, only then this will be implemented. Okay, so yeah, that's what it is. And so in conclusion, ZNodes are a powerful and flexible construct in ZooKeeper, which enables a wide range of distributed system patterns and behaviors. By understanding the different types of ZNodes, their metadata and their operations, we can design robust, scalable and fault tolerant systems that leverage the full capabilities of ZooKeeper. Okay. So yeah, this completes the ZNodes, and I have to make one more video to talk about ZAB, which is ZooKeeper Atomic Broadcast. Okay, I'll make another video on this, and then we will be completely done with ZooKeeper, hopefully, until or unless I learn something new about ZooKeeper, then I'll have to make more videos. Okay, so yeah, I hope this gives you a good understanding of ZNodes. In the last video, I only talked about ZNode at a very high level, that ZNodes are something which exist in ZooKeeper, but this video gives you a good understanding of ZNodes, why they are used, how they are used, what's the structure they follow, what are the operations they do, what's the metadata they hold, a lot of things. Okay, so yeah, please let me know if you liked the video, or even if you didn't like the video, please let me know so that I can improve. Your feedback will be very important for me. And yeah, that's all there was. Thank you for watching. Please remember to like, share and subscribe. I will see you in the next one.